My name is Beatrice Polonia. I am currently at the University of Reading, and where I am a professor of mathematics and also the director of a Center for Doctoral Training. So my work is focused around the study of nonlinear partial differential equations, or the nonlinear models that represent mathematically the phenomena, the physical phenomena of the real world. In the last 5 years, a bit because of the accident of my location in Reading, where there is a very, very strong and world-famous Department of Meteorology, I started co-supervising PhD students with meteorologists on problems that related to geophysical fluid dynamics rather than just water dynamics or wave dynamics. And I got more and more interested in the mathematical aspects of the representation of these geophysical fluid dynamics.
My name is Chris Jones. I'm from the University of North Carolina at Chapel Hill. I've been there 13 years. I'm also director of the Mathematics and Climate Research Network, which is a National Science Foundation funded network in the United States across the whole country. My area is really applied dynamical systems historically. I became more interested probably in about 2007 in climate studies. This was initiated by the IPCC report that came out at the time, Fourth Assessment Report, and it was Al Gore's movie, and climate issues were in the air, and I heard a bunch of talks that were indicating to me strongly that mathematics was somehow needed and was not really at the table in climate science. And this spurred me into the area.
I'm Baylor Fox Kemper. I'm a professor of Earth, Environmental, and Planetary Sciences at Brown University, which is in Rhode Island in the United States. I am a climate modeler and a physical oceanographer. My early training was in physics. And as I got interested in the changes that were going on in the world around me, I got more and more interested in working in this societally important science. What I think is challenging in climate science, and in particular oceanography, is that we have relatively little data to constrain both our understanding of the climate system, but also the models we use, and really, models are our prime tool for projecting into the future what's going to come. We get stuck in these kinds of quandaries in between what we can know from observations and what we tend to think from the way our simulations work. So for me, one of the primary challenges is to develop better mathematical, statistical, numerical approaches to try and ameliorate those differences between the frequency and quality of the observations and the models that we use to understand them and to place them in context.